Hey, what's up everyone? Today we're going to be talking about vector-valued functions and curves. Let's get started. Let's say we take two shapes that intersect each other. How can we find the curve of intersection between these two shapes? We do this by using a system of equations and plugging and chugging so that we ultimately get one vector dependent on t. Let's do an example together. Find the curve of intersection of the two shapes z equals x squared plus y squared and y equals x squared. To start, it might be easier if we draw the pictures first so that we have a visual to go with our problem. And since we're all amazing students and memorized the 3D shapes from the previous video, we know that the first shape is an elliptic paraboloid facing up, and the second shape is a parabolic cylinder. First, let's construct a system of equations. We have a y here and a y here, so we can replace this y with x squared and get x squared plus x to the fourth. Now let's make a vector-valued function. Recall that a vector-valued function is a function that is dependent on t, or time, and is represented by a bunch of vectors. We need to parameterize. Assign x equals t. Since x goes from negative infinity to positive infinity, we assign that to t. Now our vector looks like this. We need to fill the y and z components. Note that y equals x squared, so it follows that y equals t squared. And z equals x squared plus x to the fourth, so z equals t squared plus t to the fourth. Thus, our vector-valued function is t squared, and t squared plus t to the fourth. Now that we have this equation, let's introduce a new vector-valued function, the tangent vector. Recall from previous courses that the tangent of a curve can be found by finding its derivative. This is the same here. R prime of t is found by deriving each component individually. Going back to our example, what is this tangent vector? Well, let's just take the derivative of each component. We get 1 on the x, 2t on the y, and 2t plus 4t cubed on the z. And we get this function. For example, if we put t equals 1, we get the tangent vector specific to that time 1. So in other words, r prime of 1 equals 1, 2, 6. Now that we have our tangent vector, how can we find the vector going in that direction but of length 1? This introduces the unit tangent vector, and this directly comes from the unit vector discussed in episode 2. We divide the tangent vector by its length to get the unit tangent vector. Going back to our example, let's find the unit tangent vector, which equals the vector divided by its length. Well, we'll put the vector on top and its length on bottom, and since we're amazing students and we already know how to find the length of a vector, it is this monster. And this is the unit tangent vector, or in other words, the tangent vector of length 1. Now for a review. Find the curve of intersection by plugging and chugging and parameterizing the new function with t. We can find the tangent vector of this new function by deriving each component. Furthermore, we can find the unit tangent vector, or the vector of length 1, in the direction of the tangent vector. Here is an example you can do on your own. For the answer, click here. And remember everyone, understanding the concepts is only half the battle. Make sure you do plenty of practice to really hone these skills and master the material. Thanks for watching.